Hello everybody. During this video we will examine a microsystem platform which can be fabricated in PolyMUMPS process for educative tests using micro-tuning forks. A tuning fork is a widely known structure used as an acoustic resonator. It has a U-shaped form by two prongs made of an elastic material. When a tuning fork is struck with other object, it resonates and produces a very pure tone. For this reason, it is used for several applications, which includes musical instruments tuning, oscillators for digital systems and clocks, gyroscopes, and medical hearing tests, among others. The tuning fork oscillation frequency depends basically on its prong mass and length, and this equation is a good approximation to calculate it. However, the initial vibration is also composed by other high overtones, which are damped with time. Here, we can see other vibration modes. The second, the third, and the fourth mode. In fact, there is an infinite number of modes with different frequencies and wave shapes. However, the first is the fundamental mode and has the lower frequency. Now, why fabricate micro-tuning forks? Let's analyze first a micro-tuning fork. For example, a steel A-note fork which resonates at a frequency of 440 Hz. The prong has rectangular shape of a square centimeter. Then we can calculate the required length, which results in 13.7 centimeters. But what if we want a fork for ultrasound vibrations? Perhaps to tune a musical instrument for a dog. Anyway, let's say we want a 60 kHz frequency fork. Then the required length using the same equation is 1.17 centimeters. Almost a prong with a cube shape. Sounds weird. Let's make it longer, for example 10 centimeters, and recalculate for the area. Now this leads to 72.7 centimeters, extremely wide and unreasonable. Maybe the material is the key. Let's use again a 1 centimeter per 1 centimeter per 10 centimeters prong to be able of carrying comfortably our tuning fork. We recalculate and we realize that the material with a stiffness of 1.1 petapascals is required. Impossible, considering diamond has a Young modulus of 1050 gigapascals. Finally, what happens if we use these dimensions for a classical material for MEMS, which is polysilicon? Pretty close, right? The last calculated frequency is produced by scaling effect. In general, this equation defines the fundamental frequency. If linear dimensions are scaled by a factor s between 0 and 1, then the volume is scaled proportionally by a factor of cube s. So, it decreases at a higher rate than length, width, and height. The frequency is inversely proportional to the mass, which depends on the volume, so this scaling improves the frequency, so the MEMS tuning forks have a higher performance than quartz resonators.
In this slide is presented a resonance mode oscillation of the electrothermal actuator. The main idea is make an electrical current pass through the prong. In fact, by the Joule effect, the temperature of the material increases and, as a consequence, the length will be bigger and prone a deformation of the structure. If we produce a deformation of 6 micrometers, could be detected using a microscope, and the frequency of oscillation should be near to 60 kHz. In this example, another important scaling effect can be noticed. The thermal energy storage of an object is calculated by this equation, which is proportional to the mass and, hence, is scaled also by cube s. If we also remember that all the three heat transfer mechanisms involve area, these effects are scaled by square s. Finally, this equation also tells us that the heat transfer rate decreased by s factor. So, the thermal systems are quicker in microscale dimension. Now, a different form of stimulation is presented. That implements electrostatic force. The idea is to pull the prong using a lateral actuator. The efficiency of the method lies in the overlap area between the actuators and prongs. In this figure, the displacement produced by the lateral actuator is presented. The device is configured with another actuator that is formed by the poly-zero layer. In this case, the overlap area is larger than the lateral actuator. In fact, the force and the displacement will be also larger. The oscillation of the tuning fork could be produced by an electrostatic actuator. In this case, the force is in function of the air, area, voltage, and the distance. At this figure, we can see the force when the area is changed and has a linear behavior. But when the voltage or area is changed, the performance is polynomial. We can produce an acoustic resonance in the second structure produced by the resonance of the first. We know the resonance frequency of the first structure that was fabricated with poly 1 layer. The second structure is proposed by poly 2 and has a metal deposition in order to make an optical detection of the oscillation of the second structure. Following the design rules, the layer of poly 2 couldn't have the same dimension of the poly 1 layer. Also, the thickness of this layer is small. In fact, we need to propose a new geometry that has the same resonance frequency than the first structure. A possible solution could be propose different length of the prongs studied by the resonance frequency. At the plot, the frequency desired and the behavior of the frequency in function of the length of the prongs is presented and is approximately 66 micrometers. The detection of the oscillation could be detected by the scattering of a laser light. The main idea is that a mirror material produces the deflection of the light and a position-sensitive photodetector will be the responsible to measure the oscillation.
This layout is the final assembling to test the effect of sympathetic resonance through air. As calculated with a finite element simulation, an acoustic pressure is induced in the second fork and might result in an oscillation. This oscillation, in the frequency of one vibration mode, is not destructive and increases its amplitude during time until it reaches its physical limitation. The interaction can be better observed here, where a motion-oriented normal to the substrate is used. The first tuning fork is actuated and the second tuning fork moves from sympathetic resonance. A metal layer here is used for test with an optical setup such as laser Doppler vibrometer. Another way of studying the vibrating structures is by using the third available structure. Here, two coupled tuning forks are connected through a circular arm between the U-shaped pins. Here, we have the full layout of the chip. Remember, orange areas defines poly 0 layer, red defines poly 1 layer, gray defines poly 2 layer, and finally black defines metal layer. Summarizing, this is the electrothermal resonator, which also might be used as actuator. This is the electrostatic resonator with optical detection, and the last one use an electrostatic actuation and detection. The microtuning forks are interesting structures and can enable several applications, such as microsensors and oscillators. Here, we have an example. Do you remember that the frequency is sensitive to the mass? If an extra mass is deposited in the prongs, a frequency shift can be observed, and a mass sensor might be built.
As a conclusion of the class, we're able to say the simulation that can be implemented to the tuning forks are viable, because it's possible to study different phenomena that involve to the structures presented. For example, it's possible to study the resonance mode, the amplitude of the oscillation when a stimulation by a force that changes in the time with the resonance frequency. The prototypes proposed follow the PolyMUMPS design rules. Each process has specific rules that should be considered during the design. Different processes of fabrication allow us to generate different geometries, but it's important to follow the rules because it's a guarantee that the device could be fabricated. The devices proposed are used to demonstrate different principles of tuning fork theory. For example, considering different thickness of each layer, it's possible to design different geometries with the same resonance frequency. The principle of actuation of different devices proposed also the technique that could be used to measure the performance of the tuning fork. The laboratory practice are in function of the laboratory equipment. It is possible to implement an equipment that allows us to detect capacitance change, optical detection. Also, the sensitivity of the measured equipment is important. Thank you for your attention. If you have further questions or comments, feel free of contacting us using the following email address: